Well, hello everyone. Today we are going to talk about a new topic, which is basically hash tables. Now, what is a hash table? Before we get into that, let's just go back and talk about searching algorithms in general. Now, so far we covered two types of searching. We have the linear search and we have the binary search. Linear search basically means you're going to have to scan your array or your data structure or elements by element until you find your elements that you're looking for. And we said that the big notation for this type of search is basically n. And it's n because you have to scan the whole data structure to find the data you're looking for. And that element they're looking for could be at the end of it. So the worst case scenario is going to be at the end. We also talked about the binary search. And the binary search basically requires the data to be sorted first. And then I'm not going to get into the details because this has been covered so already, but again, with every iteration, you're basically going to eliminate half the size of your data structure, and for that reason, the big O notation for the binary search is big O notation of log n. Now, those two algorithms, they're easy, they're simple to understand, and we understand the big O notation for them. Now, the question is there any way I can have a search algorithm that will give me a big O notation of 1? And yes, that's what I said, 1. That basically means I'm not searching. I just know where's the data that I'm looking for. I'm just going to go and take it out of the data structure. The answer for that question is basically yes. We do have a way that we can make the big O notation searching to be a 1. And that's basically by using what we call a hash table. Now, the idea of a hash table is very simple, and the graph here basically explains it. I'm going to use pairs, let's just put it that way. That's basically my data structure, it's pairs. And in this pair, basically, we have the first element that will be the key, which must be unique, let's just put it that way. And the second value is going to be the value itself. It could be an object, it could be a primitive data type, it could be anything. So we have a pair. The first one is the key, which is unique, and then we have the value. That's how simple it is. And we have a lot of those pairs, let's say an array of these pairs. Now, what I'm going to do, I am going to create, or the hash table actually, or the hash coding algorithm states that if we can create what we call a hash function, where you enter the key into that hash function, and as a result, you will get an integer. And that integer will represent the index where you're going to store the value of that pair. And that's basically what it is. So I need to have what we call, I'm going to have a hash table, and the table basically it's an array, and that array will have a specific size. And then I'm going to start mapping the values that I have inside that hash table by using what we call the hash function. The hash function will read the pair, extract the key, apply some calculation to that key, and again, that key could be a string, could be a character, could be anything. And then it's going to produce what we call the index of that hash table. And then you just go to that place and you store the value you're looking for. So when you want to search for a value, basically all you have to do is to calculate the index using the hash key, and then whatever the value you're going to give you, you just immediately jump into that location in that array and you will find your value. So there's no need for scanning in that case. Let me just give you an example. Imagine I do have this array. And imagine I have 4 memory locations. Let's just or maybe more. Let's say I have this pair of values. Let's say 7 or A7, for example. That's a string, and that's my key. And I have the value that I want to store, which is basically 100. So what I can do, basically, the hash function, basically the hash algorithm basically means you take the key, you apply it to your hash function, which is again something we're going to talk about later. So this key will get inside the hash function. As a result, you will get an index. For example, you'll get the index of 2. So you go to the memory location 2. Let's imagine this is 0, this is 1, this is 2. Let's imagine this is 2. Inside 2, you store 100. Now let's imagine later on you were looking for the value 100 in this table. What I'm going to do, I'm going to take the key here, again, using the same hash function, and that hash function will give me the index 2, so I know that the value of 100 is stored in the memory location 2, or index 2, and all I have to do is just to go to that index and get the data that I'm looking for. I didn't search, I didn't eliminate anything, I just immediately just performed a simple calculation here, and that simple calculation produced an index, and that index is used to have access to the data. So hash table basically, yes, this calculation here basically is not that complicated, and it doesn't include any for loops. What includes for loops is the creation of the table itself, which basically you're going to have to do it one time, and that's it. But after creating the table, searching will be a big notation of 1, which is, again, a really big deal. Now, of course, you may ask, how can life be that beautiful and simple? Well, I'll tell you that's not the case. We do have a lot of problems with this technique, and we do have the solutions for those problems, so we're going to cover all that in a sec. But what I'm trying to say here is the idea, which is very simple. You'll have a data structure of pairs. Every single pair has a key and a value. You're going to have to create a table, we call it the hash table, which is going to be having specific size. And then after that, all you're going to do is basically to create the table is to read the keys, apply the hash function, you get the index, and then you store the value in that index. You move to the second value, and you keep going that way, keep going that until you populate your hash table. Right after you're done, if somebody's searching for any data, all you have to do, that data basically is associated with it. Is presented as a pair. So you take the key, you apply the hash function again, you give you the index, you go to that memory location, and you get your data back. Now, just like I'm saying here, imagine 100 here is a student object with all the information related to that student, and imagine this is his student ID number. This is my pair. So if I just know your student ID number, and I apply the student ID number to the hash function, I can find you in no time, a big notation of 1 inside my array. That's how simple the hash table is. Now let's go back here and we'll get into more details. Now, as you can see here, the two challenges that we have here is the size of the hash table, which again, you don't want it to be a really big one, and you don't want it to be a very small one for a lot of reasons. And also, what is the best hash function I can use? Well, let's go ahead and try to answer those questions. Now, here we have an example, and imagine you have characters. I can use the characters as a key here and make sure that they're not going to be duplicated. Now, each character by itself could be represented as an index. It will have a value. And based on the number of characters that I have, I can decide that I will create a hash table that size. Here is just talking about the first 128 ASCII codes, and I can use their characters' decimal value to have access to the index, but this is not the perfect way actually to go with. Here is just going to show you that the ASCII code tables that we're having here, the values are going to be which are 128 unique values. Again, if we're just using the ASCII code values only. But again, we have another option, but what if we use the all Unicode characters available? Well, basically, that's the number. So this, basically, it's a huge table to create. Even though we know that we're not going to be searching, but the size of the table is a little bit big. So what we usually do, especially if we know that we maximum will have, let's say, 200 characters or 100 characters, whatever the size or whatever the value that you can get, you basically modulate with the size that you want, so you can basically guarantee that you will be in that area. I'll show you examples about that in a sec. But the idea here, let me just summarize it. Whenever you create a hash table, the size of the hash table basically will be a little bit smaller than all the possibilities. I'll just give you an idea. If I want to create a hash table for every single person who has a social security number, how many possibilities of different social security numbers we will have? Well, it's basically the factorial, I believe, of 1, 2, how many characters do we have? We have 4 and 3, 7, and 9 characters. So there's a lot of combinations that could have. So that basically, if I want to guarantee that every single person will have his own place in that hash table, that's the number of of the array that I need. Well, again, who said that I'm going to have all the people in the United States in that table? Maybe just the people in this Missouri state or Kansas City. So basically, the number of the range of the values that I'm using here, which is the social security number as a value, the range could be really, really big. So if I want to start from 0 all the way to the end of the range, I will have a very big table. But what we do usually, we would use the size of the table by modulating the key value that we're going to have produced with that value. Of course, again, I'm going to show you an example about that in a sec. So modulating here is a big deal that we're going to use it a lot to control the size of that table. Now, what I'm going to show you here, this is just, again, another example to show you how important it is to do the moduling. And well, actually, this part here is not to show you the moduling part, but it's just going to show you that when you modulate, you may end up with a problem. Again, let's just imagine here again. I do have key values, and the key values that I'm using will range from 0 to million. Now, if that's the case, I can create an array of million elements. Now, again, that's against memory management here for a simple reason. I know the range is from 0 to million, but what if I just have five people in that table that I'm trying to create? Just 5 people. I know the range of the values could be from 0 to a million. So what I'm trying to do here, I'm trying to have that millions size of array. So each one of those values is going to be basically mapped to a specific value in that million array. As I said, that's against memory management. So what we do basically, since I have only 5 values, what I'm going to do, I'm going to module the million, the range that I have here, with 5 or 6 or 10. When you module with 10, basically you're going to reduce the size to whatever the module value that you're using. Now, that will lead to the second problem that we have here, which is basically what we call collusion. Collusion basically means sometimes you have 2 keys, and after you apply, this is very important, after you apply the hash function to it, you end up having an index for both those values to be the same. What does that mean? Let's look here. This is, for example, the decimal value. What we're talking about here, we're talking about the 2 letters. Where are they? Yes, here. This letter, which I don't know what it is. It looks like it's an N, but it's not an N. And this close up parentheses. Now, the value, the decimal value for the parentheses is 41, and the decimal value for this character is 241. As I said here, if I want to have a table that will include all the characters, then I need to create an array with this size. But again, that's way too big. So what we try to do here, we try to reduce the size from this number to be only 200. How do I do that? Again, just modulate it with 200. Now, after you modulate it with 200 and you applied it here, you get an index to be 41. And when you apply the same function to the second character here, you got 41. So what's this telling me? This is telling me there's 2 characters, and both of them will have the index of 41. And this is the problem. This is collusion. What am I supposed to do here? I'm trying to build my table, and I'm getting 2 values after I apply the hash function to the keys. Both of those values are pointing to the same index. Well, let me just tell you at this point, this is the biggest problem with index, with the collusion. Sorry, with hashing. It's called collusion. And no matter what you try, you will get collusion. Let's just put it that way. What we can do here basically to minimize the collusion, and there are solutions for that. And basically there are 2 solutions. The first one is called open addressing, and the other one is called chaining. And there's a lot more solutions, but in this book we're just going to focus on both those 2. And let's see here, those 2 functions, before we get to that point, yes, the collusion, as I said here, two solutions, and I'm going to talk about them later. Now, till this point, we know that we will have a data structure of pairs. We're going to take the key for these pairs, and we're going to apply a hash function to it to produce indexes. We're going to create what we call a hash table, and the index that are going to be produced by the hash function will be used to map the values of those pairs into that array, which is the table, hash table. Now we said, how do I choose the size of that table? Well, if you want to avoid collusions, you basically need to have the whole range of values. So, for example, in the ASCII code characters, basically there are that much of Unicode characters, so we basically need to have one for each to guarantee that each one of them will have its own index. Now, this table is way too big. That'll be number one. Number two, this includes a lot of other languages. What if I'm just using English language, for example? Then you will notice that this hash table basically will have a lot of spaces that's not used. And again, that's a waste of memory. So what we'd like to do, we like to reduce, we know that this is the range, this is the maximum value that a key could have. What we'd like to do, we'd like to reduce the size of that hash table. It's not a good idea to have the hash table to have the same size of your data structure. This is it's a dangerous game. At least make it a little bit bigger. What I like to do to double it, for example, or make it multiply by 1.5, just to increase it a little bit. So, what we're going to do basically to reduce the size of the table, we are going to modulate with the new size that we wanted. So basically, we know that we will have only 200 values in that table. Now, modulating it, basically, it will give us the benefit of reducing the size of the table, but also will produce the collusion. Collusion, basically, when two key values will produce the same index. And we said we have two solutions for that, open address and chaining. Now, let's put that on the side, and we'll get back to it later. And let's talk about the hash function itself. Well, there is no key here when it comes to hash functions. There's no formula that you can follow to give the hash function. It's basically experimental process. And your job basically is to find a hash function to random distribution of the values, so you can guarantee that the collusion will happen to the minimum. That's the whole the whole goal of this hash function, to make sure that the data will be distributed through the hash table, and you'll have the minimum collusion that is possible. Now, there's a lot of possibilities. There's a lot of hash functions, and it's basically, through years, they came up with some conclusions about what would be the best hash functions to go with. And the idea here is very simple, and this is basically what we're going to use here and what I want you to think about all the time. Now, number one, usually, the keys that we use in pairs are strings. That's what my first assumption here, that whenever you go with a pair, you'll have the value to be an object. That could be, let's say, a car, a home, a student, something. But the key usually is a string. And that could be a student ID, could be email, could be phone number, but usually it's a string. So this formula here could be used to produce the index. This could be used actually as a hash function, the hash function. And the idea here is basically you take each character of that string, you multiply by 31 to the power of the number of characters, and then you move to the next character, and you multiply. By the way, when I say character, I'm talking about the decimal value for the character. And then you move to the second value, and there's the plus between them, and you multiply it again by 31 to the power of n minus 2. So you see the size here was going to be reduced. Again, even though n represents the size, but the whole thing, n minus 1, n minus 2, represent the location of the string, of the character inside that string. And you keep going until you get to the first character or the last character here, where there's nothing to the power of. This formula here has been tried and studied, and they found that this will give you the best solution, and reclusion will be happening to the minimas. And of course, the value of 31 was chosen because they found out if you go with what is it called here? Prime numbers, that will basically produce less collusion. So let's just look at the CAD example here. C multiplied by 31 to the power of 2, because again, remember this is the location of the C. Basically, it's the opposite of the 2 here represent the number of characters minus 1, and then the A multiplied by 31, and here is like 1 here to the power of 1, and T here is multiplied by 31 to the power of 0, which is basically a 1. As a result, this is the value that's going to be produced out of adding all those. Now after that, I just need to module this with the size of the hash table that you want to create, and that basically would give you the right index for that value. By the way, I do have two code that I created, and I'm going to show you how the implementation in a sec. So this is basically what we're going to be using here. This is the hash function. Of course, if you can bring another one that was better than this, then go for it. That would not be a problem. Okay, so let's keep going here. What is he saying here about the integer values? I think I already covered all this. Function generations and what to avoid. Okay, now we're going to talk about, let's go back to collusion. And we said collusion could be produced or happen when two values, and when you apply the hash function to it, you basically end up having the same index. So we said there are two solutions for it. The first one is open addressing. Now open addressing basically is very simple. After you calculate, what we're going to do for the array, we will have the hash table will have what we call a dummy value. A dummy value basically is going to be used to indicate that this element here, or this the element of that index basically is not occupied by any values. In my example, I'm going to use a space as a dummy value. Now, when you assign a value inside the hash table, you'll replace that dummy value with the new value that you have. What if another time you tried with another value and you got the same index? Well, when you go to that value, you will find it's actually occupied by another value. So what do? You look for the next available value. Again, the index is not going to be the same. The index is not correct, but you're just going to go ahead and look at the next available. If that next element inside that array is actually occupied, you go to the next one, and you go to the next one, and you go to the next, until you get to the bottom of it. Now, if you get to the bottom of it and there's no values, you need to go and start. There's no space to store the new value. You go back to the top, and you keep going until you find an empty space to store the new value. Now, with that being said, I'm basically telling you we may end up moving from a big notation of 1 to a big notation of n. And that's the biggest problem with open addressing. But again, remember, if you have a good if you have a good hash function, then collusion will be reduced. So, I'm not going to go through the implementation of here. I'm just going to jump into this slide here that'll explain the whole concept. Now, what I want you to look here, I do have 1, 2, 3, 4, 5 values of names. The hash function basically produced those values that you see here, and then I had to module with 5, so the hash table here will have the size of 5. Now, I want you to look here. At the beginning, we start with Tom. You apply the hash function, you get this value, and you module with 5, and you got 4. So you go to the index 4 and you store Tom. There's nothing there, you store with no problems. Now you go back and you move on to the second value, which is Dick here, and then the value here, the hash function will produce that value. We module with 5, and here we go. We got 4. You go for 4 has already been occupied, so basically you have to go to the next value. Well, there is no next value here, so you're going to go back all the way to the top and store it here. That's an empty space. Now after that, you go to Harry, and Harry here basically will have this hash function, and after module 5 you get 3, and basically this is where it's going to be stored. No problem. Now we go back to the Sam. Now Sam will have this hash function, and then you model with 5, you got 4 again. So you go to 4, well, it's already been occupied, so you go to the next available value, which is Dick here, which is occupied, so you go to the next value, which is 1 here. It's not occupied, that's where you're going to store, what is it called, Sam, I believe. This is just to show you the process, and now you got Sam in the right place. Right after that, you got Pete here, and P basically has the hash function of that value. You module with 5, you get 3. Now, where's 3? Here's 3. So, since 3 is already occupied, you go to the next available value, which is 4. It's still occupied, still occupied, still occupied, and you end up having Pete to be stored at index of 2. Now, let's just think about that. If I give you this hash table, and I gave you the value I'm looking for, which is Pete in this case, and you use the hash function, and that basically took you to 3, and then you compare it. You basically have to compare Pete with whatever you have here. There's no match. You move to the next value, to the next value, to the next value, to the next value until you find it at index 2. As you can see here, I moved from a big O notation of 1 to a big O notation of n. Now, this is just to show you the worst case scenario. Now, if I just double the size of the hash function here, I can guarantee you probably may not get any collusion. Always going to happen to the minimum. And even if it happened, you're not going to have to scan the whole array to find it. Probably it's just going to be the one next to it. And that's basically how hash function with the open addressing works. And this here, just to show you, if I double the size here, and I'm just going to go straight to it, and as you can see here, Tom will be stored at 3. Here we go. Dick will be stored at 5. Here we go. Harry will be stored at 10. Here we go. And Sam's going to be stored at 5. Here, where's Sam? Well, we already have Dick at 5, so Sam's going to be stored at the next value, which is 6. And finally, Pitt will be stored at 7. So you can see here the size here played a major role on improving the search. But again, what is the problem then? What are we did? Well, basically, you have to give up something, of course. So those spaces basically are not going to be used. It's a trade-off, of course. The more space you have, the less collusion you will have. And even when collusion happened, you probably were reducing the chances of you to have to search the whole array to find your value and end up with a big notation of n. Okay, now this is basically how the open address works. Now, we do have operations that we need to understand. Now, I'm not going to show you those operations. It's going to be part of the lab assignment for this week. But again, how do I visit the elements of hash table? Well, it's just an array. Remember, it's an array. So just a simple for loop will give you everything you want. Now, the question is, how do I insert? Which is, again, let's imagine I want to insert a new value here. Well, basically, you just have to go and use the same method we used when we inserted all the values that we had here. You take the value of the key, you put it inside the hash function, and then you're going to give you the index. You put in that index. If it's occupied already, just go and look for the other values, an empty space to store your new value. That's pretty easy. Inserting basically and traverse is very simple. Now, deleting is a little bit complicated. It's not complicated. It's basically a little bit more complicated than inserting. What if I want to delete an element? Well, just like we did before, you're going to have to go and use the hash function to find the index of the element you want to delete. Right after you find the index, for example, if I want to delete Sam, for example, I know, let's go back here, Sam has an index of 5, so if I go to the index of 5, I'm not going to find Sam, so I need to search for Sam, and I find an index of 6. All I have to do, take Sam from here and replace it with the dummy value that we were talking about. That's how we delete. Now, deleting may lead to problems. And the problem that I'm going to be talking about here is, what if I want to delete Dick here from the table? Well, deleting Dick from the table basically will take you to, lead you to delete this element here. Right after you delete that element, so you can have a dummy value here. If I want to look for Sam again, and I'm going to search for Sam, Sam basically will give me the value of 5. I'm going to go to 5. I'm going to find an empty space, and then I'm going to have to go and search for Sam underneath it. Now, the question is, would it be better after deleting Dick to move Sam to that place? That would be yes. But what if I have a lot of values? Basically, that process is really complicated if you want to shift all the values to the right index. So what do we do usually whenever you want to delete an element from a hash table? We have a process, an operation of rebuilding this hash table. And that's, again, very, very important. Right after you delete an element, what you can do, and I think reducing the table size, no, that's not. Yep, basically what you're going to have to do is just create a new table, and in the new table you start hashing those values again to the right place, and then after that, Sam, for example, will take the right place after deleting Dick. That's basically the key here. So you can actually extend the size of it if you want, or you can shrink the size of it if you want, but shrinking basically, as I said, may lead to collusion, so that's probably something you don't want to do. But we can have a new hash table, and you have those values with all the pairs, and just map all these values back to the new table, so you will get the right value into the right index. So this is basically how we insert and delete and search inside hash tables using open addressing. Now, the other method is basically called chaining. Now, chaining is very simple. Instead of, whenever you insert a value and you get an index and you find that there's a value occupied that index, you move to the next available index. How about this? Just create an array, and each element in that array is basically a linked list. And every time you insert an element and you find out that that element was occupied by a value, again, that value is a node in that linked list, so you move to a next node. And that's basically how it works. So you can see here, this is my array. And each element, basically, as you can see, it's a linked list, and each one is pointing to the other. For example, if I'm looking for Pete here, for example, the hash function will give me the value of 3. When I go to 3, I'm going to compare it with Harry, which is not what I'm looking for. So I take Harry and move on with the next pointer to the node that contains Pete, and here we go. You found it. Method chaining, again, is very simple. Try to solve the problem of collusion, but again, collusion is happening, and to solve the collusion is basically, instead of having the algorithm to look for the empty space here, just create a linked list of elements, and that's basically how that problem solves. Of course, searching is not going to be complicated. You can just basically go to the index, and then from the index you search the linked list. Deleting, basically, just like how you used to delete in linked list, you're going to have to do the same thing here. What else do we want to do? We can delete, we can insert, yeah, we can traverse. You scan your array from the bottom top to the bottom, and every time you find a value that's not null, go ahead and search through all these elements. And that's how chaining works. So it's very simple, very easy. There's actually, of course, there's a third method. It's called double hashing, which is not, you're not asked to memorize it, but double hashing basically means it's used basically with open addressing. Every time you use a hash function, and if you find that the value, the index that was produced by the hash function has been occupied by another value, we apply another hash function to find out a new index for that value. So every single element will be applied to one hash function or two of them. Okay, so this, I'm not done yet. The last part I want to talk about is basically the performing of hash tables. As I said before, we like to think about it as a big O notation of of 1, but sometimes because of collusion that may not be the case. But in general, in average, the hash table performance is a big O notation of 1. Now, how do I make sure, this is very important, how do I make sure that I will get this big O notation of 1? Well, there's something called the load factor. Load factor, again, as a value is, and you can actually calculate it here, the number of filled cells divided by the table size. That's, again, very important to understand. So let me just go back here. The table size here is 11, and the number of filled spaces are 1, 2, 3, 4, and 5. So I got 5 elements here. And that's going to be divided by 11. Now that's the form, the load factor. Now what we do, basically, we use this equation here, or this equation. Where is it? This one or this one. Now, if you're using open addressing, you use this formula, and the C that's going to produce here is basically going to tell you how many times you have to do a comparison. And that's, again, you calculate the L, which is the load factor, and then you apply this formula, and this is basically tell you how many times you're going to do expected number of comparisons to find out the value you're looking for. Of course, the lower this value is, the better it is. And all of that depends on the value of L after all, as you can see here. Now, if I'm using the chaining method, basically, you're going to have to say 1 plus L divided by 2, and that will tell you the number of comparisons that you're going to have to do. It's expected number of comparison to find the value. So after you finish the hash table and the building of the hash table, this simple calculation should tell you the number of comparisons, and again, the lower that number is, the better the hash function that you actually chose to go with. This here is just to show you a comparison between those, and it's going to talk about this comparison, which is, again, something very simple, not that complicated. Now, in this part here, it's the implementation of the hash table. Now, I'm going to skip this part. Of course, you can go ahead and read it if you want. But what I did, I created a very simple version of this code here. And you feel free to use it if you want. I'm going to go ahead and explain my and you can actually use the explanation that you have here to answer the labs, of course, but I'm going to put this on the side now, and I'm going to move on to Visual Studio, and I do have two projects here. The first one, which is this one here, I am going to use the open addressing here, and the second one, this is the chaining. Okay, so let's start with the open addressing. Of course, I'm going to upload those files later. First thing first, I created an array. And this array, the data type of the array is a pair. And this pair has a string as first data type and character as a second in this pair. And here we have a list of those pairs. And this basically is the key here. And this is the character, which is the value. That's what I'm using here. So key and values, and you can see algorithms, and then I said, let's just duplicate some values, but not the keys. Remember, ALGO. Right after I'm done, well, let me just put different values. So I'm just going to go inside C, and I'll put 3, 0. And this area here, I will put U. I just changed those values again. So this is again my original data structure. It's an array of pairs. And in this area, I am going to, this line here is just to tell me how many elements did I have in this array original. And then I decided that the size of my hash function will be 20. I created my hash table, which is basically an array of characters, because I'm interested in storing the character here. And this is, again, the size of the character. And I'm going to assign it all these elements to a dummy value, which is a space. So this hash table is going to be populated with the spaces, and the space is basically my dummy value in this case. Right after that, I created a new value called index. And I'm going to go through this array, element by element, and try to map them into that hash function table. So, first thing first, I assign the index to 0 for each element at the beginning. And this is a floater that's going to go for 3 times. I think I made a mistake here. Let me just fix it really quick. As long as it's less than 3. And this is going to be ++. This here, this line of code here is for me to calculate the hash function value. The hash value for each one of those keys. Remember, I'm passing 3 characters, so I'm going to go for each character. I'm going to take the first character, and then I'm going to multiply it by 31 to the power of that index, which is basically, at this point, it's going to be 0, and then 1, and 2. So after I did the calculation here, I will get values, or really big values. So I'm going to actually module it with the hash size, so I will get the right key for it. Right after that, I'm going to go and check. this is very important. If the hash table with the index that was produced out of this calculation was populated with what here? What is it called again? Yeah, space. Then go ahead and take the second value, which is the character, and store it inside the hash table. So if originally I got a space, then change the space with the character that you have. For example, let's imagine this calculation here produced 5. So I'm going to go to the index 5 of the hash table, and if I found there was a space, then I'm just going to replace the space with the character, which is, in this case, A. Now, what if that's not the case? Well, basically, what if there is a variable there? Here's what I'm going to do, while true. So this for loop, this while loop is going to go for a really long time. I'm going to increase the index by 1, and then whatever the value, I'm going to modulate with the size again. Now, why am I modulating with the size again? Because, again, if I get to the end of the hash table, this modulating will get me back to the top of it. So let's say the value that I got with index, which was populated where the value was, let's say, the second to the last. Well, I need to find what is after that, which is the last element. Well, what if the last one was populated? Then I have to go all the way back to the top. And then the back of the top, basically, this modulo operation will get me back to the top of that table. Now, all I have to do here, for each time I'm increasing the index by 1, again, check if it's a space, which is empty. The moment you find a space, all you have to do is just replace that space with the value that you have in the original, and then leave this while loop. And keep going value until it's done. Now, what I'm going to do here, of course, remember, since the hash table is a pointer, all I have to do is delete it. Don't forget that. Now, what I'm going to do here, I'm going to take this line here, comment here. I'm going to take this comment away just to show you the implementation. So this here will show me the first index value calculated, and then if that index was changed for any reason here, then the new index is going to be shown, and then after that, it's going to tell me what is the value stored in that index file. So let's just go ahead and run this. And I'm going to go show you how did it work. And I'll increase the font size here. And here we go. So basically, the first element that I had in the hash table, sorry, in the original data structure, basically gave me an index of 17. So inside the hash table, if you go to index 17, you will find A. And then the second value, which is L, basically the produced index was 9, and then you got 8, and then you got 4, and you got 5, and you got 7, and then you got 18, and then you got 5. And look at this, 5 and 5. Now you see here, I got a collision when I was trying to insert H, because both of R and H produce an index of 5, and because 5 was already populated with R, I increased the index by 1, so I went to 6. Now 6 basically is not populated by any value, so I got H here, and then I went to 18. Now 18 is populated by T, so I have to increase it by 1, so I got 19, and that's where M. 2 is not populated, 0 is not populated, 3 is not populated, 19 is populated by M, and I have to increase it by 1. Well, basically, this is a 20, so I don't have an index of 20, so I have to go all the way back to the top of 1 to store 0, and then 15, 15, and that's how it works. Now, let me just show you the effect of reducing the hash table. I'm going to change that to be 10. And here we go. Let's close this. So 7, 7, 9, 9, no problem. 8, 8, 4, 4, 5, 5. Look at this, 7. So I went to 8, and 8 was populated. And then I went to 9, and 9 was populated. And then I had to go to 0 to start. And then I get to 8. Well, 8 is populated, 9 is populated, 0 is populated, so I have to go to 1. 5. Do I have 5 here? Yes, I do have 5 here, so I can go to 6. 6 is not populated, so I get H. 2. Look at this, 8 again. 8, so I went to 9. 9 is populated. There is no 10. There is 0 populated. 1 is populated, so it's going to be a 2. And now since 2 is populated, the 3 will go here, and that's it. Oh, where's this coming from? Did I make any mistakes somewhere here? It worked perfectly with a 20, but it didn't like it when I typed 10 here for some reason. Let me make it 11. Still, I'm not sure where's this 1, 0 coming from. This is supposed to be, yeah. Oh, wait a minute. So this 10 here represents the index, but for some reason I'm having an infinite loop, which is basically here. This is causing this infinite loop for some reason. I'll fix it when I later in the upload to see why is it going that way. But for now, let's just go and put it back to be 20. Right after I fix it, I will just put a comment on it when I upload the file. So this is basically how the open addressing works. So I'm going to go ahead and put these comments here, and I'll fix this in a second, send you the correct value. Now, let me just go down here, and let's move on to the next value, which is basically the open addressing, the chaining. As you can see here, so far everything's similar to the first one. The difference here is basically, again, I got the size figured out. I got the size of the hash table, and look at this. This is my hash table, and the data type is a list of characters instead of just the characters. And just like we did before, calculate the index, very, very straightforward, similar to what we just did before. And right after that, all I'm going to do is push back at that index, push back the character at that index. So if that element was already populated with a value, then it's going to go and move it to the next element. See, it's a lot easier comparing to the open addressing. Now, if you look here, this part here is just to show you the results of the implementation. I'm going to run it. And let me increase the font size here. And you can see here, this is the size of my array. A, null, S, null. Oh, here we go. This is a collusion. Basically, R and H has the value of 5, and for that reason, I got R, and then I got H, and then after I got null. 7 here, I, G, 9, nothing, nothing, O, nothing. Here, we got another collusion at 18. You got T and M and G. Let me try to change the value here to be 20, 10, or 11, and I'll get back to fix the other one later. You'll see that the chains probably will be a little bit longer. Let's see if that's the case here. Well, I got, here we go, 3 characters in one list. And we got a lot of more. So you can see the size here plays a major role on the number of comparisons that we have. This here didn't have any problems with the changing of the size. The other one did have a problem. So this basically summarizes what this chapter is all about. I'm gonna, the lab and the assignment for this week will depend on using those 2 files. I'm just gonna ask you to create functions to get something done there. That will be it for today, and I'll talk to you guys later. Bye.